We are encouraging students to have a startup company on their own. Our vision is to be recognized in both teaching and research.
So, greetings everyone. On behalf of IIT Madras and AARDO, I welcome you all to the day 2 of the online training program. So yesterday we had a wonderful participation, and we expect the same enthusiasm from all the participants. And so today's session will focus on the topic technologies enhancing productivity of small farmers. And now let me welcome Dr. Palniappan Ramu from Department of Engineering Design, who will be the moderator of today's session. Brief bio of Dr. Palniappan Ramu. So he's from the Engineering Design Department, IIT Madras. He holds a Bachelor in Engineering and Design from Mechanical Engineering and a PhD in Aerospace Engineering. And now he heads the Advanced Design and Optimization and Probabilistic Techniques Laboratory. So over to you, sir.
Naresh, before I start, I just want to make sure there are 2 black patches on my screen. Is that how everyone else is seeing it? Or?
Now do you see it, sir?
Yeah, it's
Yes.
still there.
Oh.
Yeah, the lower one has become smaller.
Okay.
As long as others are not seeing it, it's perfectly fine.
Okay. It is same for us, sir.
Yeah, so if they are showing something, I don't want the speaker's message to be blocked by these.
Now is it fine, sir?
Now, yeah, the lower one has disappeared, but the top one, it's sort of
shrunk a bit. Yeah. But actually,
no, it's gone back. It's gone back to its original. Okay, so when you are trying to do that, let me just get started. Let me welcome you all on behalf of IIT Madras and this effort. So today we have 2 speakers, Dr. Satya Chakravarti from the Department of Aerospace Engineering and Dr. Sridhara Kumar Narsimhan from the Department of Chemical Engineering. So this session is about how technology can be used to enhance the productivity of small farmers. India, which is predominantly the economy is driven by agriculture, and I don't know the exact percentage, but majority of them are small farmers. We are not like the West, where a single person has a huge farmlands. India is composed of in the small villages, we have like small farmers who have probably less than an acre or few cents of land on which they cultivate. And this has been a challenge to see how we can improve the productivity of such farmers, because mechanization is just one part of the solution, which is typically useful for large farms. But for small farms, we need like customizable solutions. And the challenge here is the cost. It has to be very attractive from the cost perspective. There cannot be any compromise from the quality and the performance perspective. But at the same time, it should also improve the productivity of the farmers. So this has been a very challenging area for a country like India, where the agricultural sector, especially from the produce perspective, is hugely unregulated. Based on my experience that I've worked with people, it is hugely unregulated, though the government gives predictions about the rain, the seasonal changes, and what could be the demand in terms of the crops. And they have the mandi to facilitate the farmers who produce and the buyers to match them. Still, there have been challenges, and this is one area where technologists like the two speakers today could probably help us, help the situation. And one of the major challenges in a country like India has been the water. It's of course the availability of water, and the other one is the intelligent use of water. Oftentimes it's about the awareness part of it. So the other one is about how do you use the fertilizers or urea, as it's usually called, because typically it is blindly used. Instead, there are like emerging ideas like precision agriculture or stress-based, crop stress-based watering and fertilizer introduction to the soil. So I guess the next two talks are broadly going to touch up these areas. With that introduction, I look forward, just like you, to the talks of Dr. Satya and Sridhara next. So the first one to go up is Dr. Satya Chakravarti from the Department of Aerospace Engineering. He has an undergraduate degree from IIT Madras. He has gone elsewhere to do his PhD, came back to IIT Madras. As you can see, he has several awards to his name, but that is something to the context that he's going to talk today. He's also advising a few startup companies, or rather he's a co-founder of a few startup companies like Agnikul and ePlane. And I believe he's going to talk about one such concept where drones can be used to spray maybe the fertilizers or the insecticides. So over to you, Professor Satya.
Good. Thanks, Palni. Let me get started with my talk right away and start by sharing my screen. Good afternoon to all of you, or good evening, depending upon your time zones, or good morning. Very happy to be here. Thanks for letting me do this. Let me just get to the presentation mode. Yes. Are you able to see my screen?
Yeah, we are able to. Satya.
Good, great. Yeah, so what we would like to talk about today is, we've got about, I guess, 35 minutes or so. So let me start by talking about spray drone technology for Indian farmers. And when we say Indian, the point essentially is we are primarily looking at Indian agricultural situation at the moment, but we believe that there are a lot of characteristics that Palani mentioned about that Indian agriculture could also prevail in other parts of the world, probably in Southeast Asian and East Asian countries, as well as in African countries and so on. So this might be useful over there as well. So right. So drones are essentially flying objects which can be controlled by humans or can fly autonomously. We will show some examples of autonomous flying later in this in these slides. The main advantage of drones in agriculture is the aerial support, where we can analyze from aerial view, which can't be achieved at the surface. The typical application of drones is in smart farming is primarily precision agriculture, where you can use multispectral or hyperspectral imaging, looking at the crop colors, and then do deep learning to understand what the growth phase of the crop is, including crop height, crop cover, and so on. So that's not what we are talking about in this. We're going to be talking about spraying, which is spraying pesticides, the weedicides, the fertilizers. There are other applications like seeding, for example, which we believe is more prevalent in very specific crops that are planted some distance apart. Typically, afforestation by planting seeds of trees is a lot easier when compared to actually planting crops as such. And of course, finally, in security and surveillance is also another area where drones could be used. But as I said in the title slide, we will be focusing in this talk on spraying. But we could actually, I think, other than seeding, we have actually done other things like imaging and security surveillance in what I'm working with. So if anybody has any questions on those, please feel free to ask as well. But as I said, the focus is on spraying. So this is one of those things that Professor Palani Ramu actually alluded to on how technologies and automation can be done or are done in the developed world or the Western world, which is usually in large farming areas with tractor-mounted sprays or aerial sprays using drones. Now, a couple of problems with this. For example, if it's a tractor-mounted, you obviously have to, so the crop keeps growing up and up and up until a certain height. If it's something like sugarcane, then the height of the crop becomes extremely large. And even if it is like something like rice, it actually starts with something like about 1.5 feet, and then it goes all the way to about a meter or a meter and a half. So using tractors, you need to actually have furrows on which the wheels can go. So it has to be very specifically made for tractors to use this, and there are limitations beyond a certain growth of the crop. Aerial sprays with using planes essentially sort of dumps a lot of pesticides. So it's very hard to control the amount of pesticide that you use, and pesticide does cost a lot of money. And so precision agriculture will also mean that you also are doing precision spending on your farming, and that's what we are talking about. So why is this large volume sprays happening in Western countries? Is simply because they have like large area owned by farmers. It could be cooperative farms or collective farms, and it could be company-owned farmlands, which could be corporate farms. In the Indian context, even if you're actually having corporate farming, corporate farming is actually done by leasing farmland from farmers by companies. So which essentially means that you still have only small farms to deal with. So in India, compared to Western countries, the area of farming land owned by farmers are less, and so different types of crops. So that's the other thing, right? So different farmers will actually choose to grow different crops, and the spraying has to be different for different crops, and it's very difficult to adjust to this. So 84% of farmers in India are medium scale, who own anywhere between 4 to 24 acres of land, and there is a substantial amount of or number of farmers which are actually small farmers, who are owning land that is even less than 4 acres. Typically, it's about 1 to 2 acres, or sometimes in some cases it's even less than an acre. So as Professor Palani was talking about, using Western technologies to India is not feasible unless it is customized to Indian agriculture, and that's what we are trying to do. So using drone technology for spraying applications, drone is a carrier where it can be customized to carry the sprayer tank and spray using nozzles. And so how do you use drones with a sprayer? So it's essentially try to combine two technologies. One is on the one hand you have a multi-copter drone, and on the other hand you actually have a long boom, and we need to see how to mate the boom to the drone and get the drone to fly. So this is our answer. So we have actually got some implementations of this of drones to be used with the boom. So here you can actually specifically see there is a box construct of a frame that carries the boom at the bottom and the drone at the top of the box frame. And we will see why we need to have the box frame under certain circumstances versus why you may not need those in certain other circumstances. There are a few aspects that we have to keep in mind, which is what this part of this talk is all about. The rest of the talk is all about. So the drone here we are looking at is primarily a multi-copter drone, which means it has like multiple rotors. And so using multi-copter drones, type of drones is suitable for spray applications, as these drones can carry heavy payload. It's not very common, so we actually devise these kinds of drones that carry heavy payload. And they are capable of hovering at a specific area or crisscrossing a very small region. So to build a robust multi-copter drone, which can withstand high wind and gust, the setup should have a thrust-to-weight ratio of about at least 2:1. That means it should be able to carry twice its own weight in order to be able to adjust to a lot of other conditions. So using larger propellers will reduce the high air speed that is being pushed from the propeller down, and hence that won't affect the spray pattern. So that's one of the key things that we will have to keep in mind, which is will the propeller flow affect the spray pattern, and is that okay? In some cases, it's okay for the spray pattern to actually be affected by the propeller flow, and in some cases, it is not okay, right? So we'll see some of those in greater detail. So we will use the brushless DC motors. We will use electronic speed controllers and propellers, which are rated approximately. I mean, typically the 48 volt is a standard for DC power, and we typically can use like a 12S lithium polymer battery, which are commercially available. So it's not so difficult to put together a drone from commercially available components. So the technique here is to make a commercially available product or a service. Our first step is to actually understand the spraying process in India. After working closely with chemical companies and farming communities, we can understand what are the current techniques that they're using. After that detailed study, we came to the conclusion that the same nozzle cannot be used for spraying different chemicals. So question is, what are those different chemicals? There are typically many different types of chemicals used in farming. Out of the different chemicals, our focus is only on liquid chemicals, because we would like to use liquid chemicals to spray using drones. And there are a few liquid chemicals that are most commonly used by farmers in India. And these include pesticides, which are aimed at killing pests, weedicides, which actually kill weed plants that grow along with the crop, but and then take away the nutrients that are meant for the crop. And of course, there are liquid fertilizers and micronutrients that could be sprayed as well. The assumptions that actually go into what we're doing are that the selection of the nozzles and chemicals depends on the crops and the soil and geological conditions. So this has to be carefully done. Our study of using sprayer drones are particularly focused on rice and sugarcane at present. So that's kind of like a limitation of the scope of what we are talking about. But we have had interactions with people who grow cotton, corn, and we have done some demonstrations in tea estates and so on. So there are quite a few other things that we have done, but our focus is primarily on rice and sugarcane. The reason for that is how the highest productivity of the agricultural crops in India includes rice, sugarcane, and wheat. So these are three. If you are able to attack these three crops, we are actually covering a huge amount of farming in India. So let's focus first on pesticides, then we'll go a bit to weedicides, and then we'll go into the fertilizers and micronutrients. Pesticides constitutes a lot of our work. The chemical used, this is the chemical used to kill pests. So how do these pesticides, the chemicals used by farmers in India directly kills the pesticide for most of the crops, but won't affect or poison the crops if used in exact concentrations or quantity. And what really matters here is the particle size of the pesticide that is being sprayed, or the particle size of the spray of the pesticide. So the particle size of the pesticide should be low so that it can penetrate deep into the crop surface and kill the pest. Challenges exist even now. For example, there are certain pests that can actually grow on the underside of the leaves. So question essentially is that is it possible for us to create a mist that will also go on the underside as well as penetrate? So this is where the combination of using what we call as a prop wash, the flow field from the propeller to aid a mist creation through vortex generation, or should we just actually penetrate with a deep spraying, right? So that challenge exists for different crops. And different kinds of pests that attack these crops typically. So the spray characteristics for these pesticides are particle size, as we mentioned, which is approximately between 90 to 100 110 microns, let's say around about 100 microns. The discharge per nozzle should be of the order of 300 to 600 milliliters per minute. What we are now looking at is fairly small, low volume spraying when compared to what is manually done. And we will go through these comparisons. What we will find is that there is like about an 80% reduction in the amount of spray that we use, or the pesticide that we use per acre when we're now trying to do drone farming, but compared to a manual spraying where you have a significant amount of dilution of the pesticide with water. So we are actually looking at pesticide discharge rates of the order of about 300 to about 600 ml per minute per nozzle, which means that if you have a boom, we could actually put multiple nozzles up to about, we have tried up to about 7 nozzles along a boom. So that means like per nozzle, we will be having this kind of a discharge. The typical pattern that we use for the nozzle, the spray nozzle is a hollow cone spray, which operates at a pressure range of about 4 to 6 bar. And here you can see a picture of a typical spray and also the kind of nozzles that come. On the other hand, if you now look at weedicides, these are the chemicals that are used to kill the weeds or herbs which grow along with the crop, and these are known as weeds. It's actually meant for the crop, and so we need to be able to get rid of these weeds. The chemicals over the leaf surface, and other weeds can be killed by spraying chemicals till the root or the soil, which essentially means that if you're doing an aerial spraying with a drone, if you have to actually reach up to the root or the soil, we need to have highly penetrating nozzles as opposed to creating the mist for a over leaf surface. So again, there is a variation in the kind of spraying that we will want to do and how you might want to exploit and utilize the propeller airflow, which is called the prop wash in this case. So the spray characteristics for the weedicides are particle size, again, around about 100 to 120 microns, and the discharge is somewhere between 300 to 900. So it's again beginning to look a little larger than in the case of pesticides. Pesticides need to be in exact concentrations. Here it's a little larger. And the pattern of the spray here is different, which is what's called a flat fan spray. So you can kind of like graze past the crop as you fly the drone over top, and the pressures here are typically between 1 to 3 bar, the injection pressures. For the fertilizers and nutrients, the ones that we are actually looking at in liquid form, we need to have particle sizes of the order of 250 to 500 microns. The discharge per nozzle is about 450 millimeters to all the way to 1.3 liters per minute, which is now fairly large. The pattern of the nozzle that we have to use is again flat fan, but this is what we call as a flood jet nozzle. Look at the nozzle types there that are used, and you will find that they are flat fan, all right, but they will have a very high discharge rate at pressure of about 1 to 2 bar. The particle size is larger here, first of all, and the discharge rate is also correspondingly higher. And therefore, the drones for the fertilizer spraying need to be much bigger and require a larger tank capacity, so that per acre you are able to deliver the amount of pesticide that you want and still clock a few acres in one go, right? So the chemical usage here basically means using specific nozzles for specific chemicals. That's the first study that we will have to do in any such operation to optimize the usage of chemical quantity for a particular crop over a given area. This is still an emerging topic across the world. I think in China, they have actually deployed about 30 million hectares of crop under drone spraying, and there are approximately about 12,000 drone spraying service operators available. And this industry actually grew within about a 3-year period between 2016 to 2019. So it's a very rapidly growing area, and there is like a lot of study that's actually happening as we speak. So using same nozzle for different chemicals will not give proper results, and using same nozzle will result sometimes in overdosage to the crops, or sometimes low dosage to the of the chemicals. So the study of nozzle from the above slides will vary depending upon the nozzle manufacturer as well. So what we have shown is only typical manufacturers of nozzles. but manufacturer to manufacturer, you will find nozzles are varying in properties. So we'll have to. Finally, what we have to look at is the discharge state, the particle size, the injection pressure. That combination is what we have to essentially look for in a given spray. So at IIT Madras, I think Palani Ramu was giving an introduction. We have in the combustion research center that I head, we have an exclusive spray diagnostics lab, which has state-of-the-art spray diagnostics capabilities. So we could actually use those capabilities to characterize the sprays that are suitable for spraying in different over different crops. Now the question is, how do you integrate the spray system with the drone? So all of the things that we've talked about so far is actually for spraying system for drones, no doubt about it. So it's not like a general spray that we're talking about, manual spray or any other means like a tractor mounted spray or something. We have been talking about sprays for the purpose of drones, but let's now talk about how to integrate the spraying system with the drone, and what are the issues involved in that. So for the agriculture, there are two methods implemented using drones for spraying applications. One of them is a broadcasting spraying type, where spraying chemicals all over the crop. And then you also have spot spraying, and this is spraying over a particular area or a spot, right? So broadcasting spray is pretty much like what we typically use out of the two types, because this is commercially viable. Spot spraying is much more precision spraying, and it has to be developed even further in order to be able to make it commercially viable. Probably have to be coupled with cameras that can locate places that need to be sprayed on the go, on the fly, literally, and spray. So and it also requires very high accuracy GNSS systems. So this has to be able to locate the drone where you want, and therefore the cost of it will be higher. So there are again two types of broadcast spraying. One of them is using a spray boom, like the left-hand side picture. The other one is the other one, although we have a boom, we have these underprop sprays which are coming down all the way near the crop. You can see those downcomers from the boom that are being used, right? In fact, the right-hand side picture may not even have a boom. It's actually the downcomers that are located at the bottom of the spray, at the bottom of the rotor arms, rather than having actually a boom, right? So how do you do the construction of this integration of the spray boom or the underprop sprays? Is to first of all get nozzles and the type of spray which have to be used in the drone, and the next is to integrate with the drone, like building a body over a chassis of an automobile. So you have a drone chassis, and on the drone chassis we have to mount these sprays, and it could be either using a boom and spray nozzles, or it could be those underprop nozzles. In addition to those nozzles, you need to have a tank, you need to have a pump, you need to have a nozzle holder, and you have to have connecting pipes. And these are, again, mostly commercially available. We will have to pay attention to the tank structure a bit, because what are the challenges here? For example, when you now look at the tank, as I was speaking, the chemicals inside of the tank will have sloshing while braking. So typically, we will have the drone go from one end of farm to the other end, and then it now stops, and then it now displaces itself to the side, and then now goes through another motion in the opposite direction from one end to the other end, and then it stops, and then it then shifts back again, and then it now, so it's kind of like rastering. So the other, of course, one of the things that we have not really talked about is Indian farms do not really have regular shapes, because I guess they've had like a lot of family disputes and stuff, so they actually split the land in many different ways, and of course the geography has to be accommodated. So you will find that they are typically some kind of polygonal shapes. They need not be necessarily rectangular or squarish or anything like that. So what we normally do is we do what's called the geofencing. That means like we take the drone and its GPS and walk around the plot of land that we have to spray, and then we now inform the the drone's coordinates that this is the region within which we will have to spray. And we can now do an autopilot, and the autopilot will essentially do this rastering within this region. And that is what is called as waypoint navigation. So we will actually now indicate these waypoints, and then we will go back and get this drone to do this rastering. So every time it actually goes from one end to the other end and stops, and then it has to displace itself to the next row, there will be a sloshing of the liquid within the tank, and the sloshing actually ends up destabilizing the drone, right? So we need to try to arrest these sloshing. So some tanks that are well crafted and well designed will have baffles within in order to try to accommodate this sloshing and try to alleviate that problem. The other next thing is about the pump. I mean, I think the numbering is screwed up there. Sorry about that. So we came across various pumps and ended up with a BLDC motor with a magnetic drive pump, which is suitable for variable pressure spray. Hello. Can I go ahead?
Professor Satya, please go ahead.
Yeah, thanks. So and then the connecting pipes could be polyurethane pipes and nylon tubes that are suitable for different spraying applications. Plant protection spraying drones are specific kinds of drones, usually with a long landing gear. So this is something that we have talked about in the context of the picture that I showed of our implementation. So this has a long, what's called a long landing gear, and a spray boom attached at the bottom, and we will show a video of this. When drones flown over crops at early stage like rice are more delicate in nature and can be easily destroyed by the high velocity of air pushed by the propeller. So you will find these crops actually go hither and thither, and that can destroy the crop in its early stage. So we want to have the propeller far away from the crop top, but the spraying has to be done near the crop top. So there must be a physical separation between the spray boom and the propeller plane, and for which we actually have a long landing gear. So greater the landing gear distance, the drone actually becomes more unstable, because if you have this boom at the bottom and that is slung at the bottom of a long landing gear, a tall landing gear, and the propellers are the ones that are actually holding the drone at the top, and so it now gives into a pendulum effect, and this pendulum effect can actually give a feedback to the drone in ways that the drone may not be able to stabilize, and it can get into some sort of an instability, and the pendulum can start swinging much more wildly than with an initial small disturbance. Right. So in order to control this, we will have to require higher thrust motors, even for lower payloads. So we talked about a thrust to weight ratio of about 2, and that's mainly the reason to control this. Right. So in the case of pesticide applications, paddy is very common to pest attack. So after a deep study with the nozzle selection and the discharge value per nozzle, we came up with a suitable configuration. So our configuration that we have arrived at is using the spray boom as a particle size is very low, which means we need to be close to the crop top, and we need to have a wide boom that will spray at different parts. We used, as I said before, we used about 7 nozzles spaced about 650 millimeters apart, and we used a hollow cone type of nozzle, and the discharge rate is about 350 millimeters per minute. And we have used tank capacities between 12 to 15 liters. And this can complete 1 acre in about 5 to 10 minutes at about a 5 meters per second velocity of rastering along one side of the farm. So here is a picture of a long landing gear, 1.5 meter landing gear with 4 meter boom. This picture is taken in our cricket stadium in our campus as a demonstration. Another thing that this will show is to want to align your casting direction with the wind, so that you can actually have a wake along the spray rather than a side drift, depending upon the wind direction versus the rastering direction. Yeah. So we have actually had a few different renditions of this. For example, this particular version, we have a inclined landing gear for better stability, right? So after continuous tuning and optimizing the design, we have been spraying pesticides for paddy crop with about 1.5 meter landing gear and 4 meter spray broom. This is a picture of one of those kind of sprays. Now, as far as the pesticide application, the conclusions are for building drones specifically for pesticides, we should use hollow cone or solid cone nozzles, where the particle size is around 100 microns. As we are using long landing gear, high power motors are required for stable flight. Using underprop type will not be suitable unless very less drift due to wind is present. So better to actually use the long landing gear version for this particular application. So for 1 acre of land, it is possible to spray in an average of about 15 liters of pesticide compared to a manual spraying of about 80 liters per acre, about 80% reduction in the volume with reduction of time by about 20 to 30 minutes per acre. I think sometimes it's even longer with manual spraying, but we could actually get it done in about 5 to 10 minutes. On the weedicide application, weeds can create a serious impact over sugarcane as they are reducing the sugarcane growth at every stage of their growth. Prevention of weed growth at early stage of sugarcane will yield very good yield. And so this is a picture of one of those farms where sugarcane is planted in a place called Nellikopam near in Tamil Nadu. So after some deep studies on weedicides of sugarcane, we came to the following configuration. We have used a flat fan nozzle type under propeller configuration, as there is a need for deep penetration inside the sugarcane till the surface of the soil. 4 nozzles under the 4 propellers, a discharge rate of about 800 ml per minute. To cover 1 acre, it takes about 10 to 15 minutes at about 5 meters per second, same kind of velocities as before. And the total volume is about 24 liters per acre. So again, this is a smaller drone that way, right?
ஸ்ப்ரே பேட்டர்ன் கவர் பண்ணல, ஸ்ப்ரே பேட்டர்ன் தானே கேப்சர் பண்ணும். நைஸ்.
Drone mata. Drone aja tangkas kasachni.
So the conclusion on this part is that lesser drift of chemicals compared to hollow cone sprays which are used for pesticides. For sugarcane, underprop configuration will be suitable as the chemical can penetrate deeper due to the propeller wash. So here we take advantage of the propeller wash. Due to high discharge of nozzle, we need larger tank capacity, and using drones, it is possible to spray 24 liters over 1 acre of land, a reduction of about 75% of liquid volume compared to the manual spray, and reduction of about 40 to 50 minutes of spraying time. So in summary, I think I'm just about on time, I guess. So drones play a major role in commercial applications, including spraying chemicals. So it helps in preventing the death of humans or health hazards when they are heavily exposed to chemicals during manual spraying. Since the propeller wash in drones, the drift in chemicals can be reduced. Since drones are reducing the time consumption, a larger area can be covered in a shorter period of time. And drones consume less chemicals, and farmers can save some expense on purchasing high volume of chemicals. This is a significant part in the farming economics that way. And higher speed, I'm sorry, I think I lost the last bit. At high speed and spraying less chemicals, drones can help in preventing overdosage of chemicals on crops. Hence, the quality of crop can be improved. I think that's all I have to talk today. Thank you very much for listening.
Thanks, Professor Satya, for this great presentation, giving us an update on what you're doing with respect to drone development for agricultural applications. I have this agenda for date 2 March 23 on my screen. And as per the agenda, we are supposed to start Dr. Sridhara's presentation at 2:50. And since I guess like we saved a little bit of time on my introduction and Naresh's introduction, which makes a lot of sense. And because of that, we have a little bit time. It also makes sense to take questions now. We'll still not be late for Dr. Sridhara's talk. We'll do that on time. So when this talk is afresh, the floor is open for questions. There are a few questions on the chat box. One of the first questions, Dr. Satya, is while using the drones, do we make dilutions or use the pesticides in the pure form?
Oh no, I think there is no straight answer to that, unfortunately. So there are people who are actually trying to do what's called as ultra low volume spraying, in which case they do very concentrated levels of spraying. Okay. Then that depends on what the crop can take. So sometimes the pesticide shouldn't be poisonous to the crop. So how much concentration the crop can withstand is what dictates how much dilution, what is the minimum amount of dilution you can do. So to give you a quick sense, it's possible that 1 acre can actually do with 1 liter, right? But we will dilute it up to about 10 liters when you're using in a drone, but we will actually dilute it to about 100 liters when you're doing a manual spray, right? So this is the kind of numbers that we have come across in this. So there is some amount of dilution in what we're doing as well, because the crop has to withstand the concentration. Or conversely,
sorry, go ahead.
Yes, indeed. So the spray nozzles will actually have to have a certain viscosity, right? Okay. So the pesticide manufacturer is the person who holds the key to all these things, right? What's the level of concentration of the chemical that they develop for the kind of viscosity that is suitable for the nozzle? If they do a good job right at the beginning, then we can tailor the dilution accordingly, and then maximize the number of the amount the acreage under spraying, right? So pesticide fertilizer developers have to develop things that are meant for drone spraying more specifically than what they have been doing so far.
So one of the few questions, other question is, are there chances of crash?
The quick answer is yes.
Chances of crash. Yeah.
Right. So the drone tech is still again not very robust. There are probably only a few commercial companies like DJI which have perfected drones very well, but most of the reason for the crash is actually the pilot. All right. And so what we try to do is to make an autonomous version of the flight. So as I said, we have a geofencing, and then within the geofencing, we have a path planning. The path planning is based on waypoint navigation. So we actually give waypoints that corresponding to the RAS setting that I mentioned. So when you try to do all that, the pilot is out of the equation. All right. So once the pilot is out of the equation, I think things happen very automatically, and there is nothing haphazard that happens. But the pilot is also required in order to take control, just in case there is something like a sudden gust or whatever it is that's destabilizing the path. And the other thing that we are also been working on very seriously is obstacle avoidance. So many times what you will also find is there are like poles that are planted in the middle of the farm, or you may have like a big tree, or you may have a well, right? So those obstacles come in the way. And then when you have these booms and stuff, the drone needs to actually have a situational awareness of how much its swath is, and it should not go and hit a pole, right? And this is actually very difficult even for a human pilot to negotiate, right? So these things will require more automation to be brought in that are more specific to the situation. And those developments are required for us to make sure it's actually more and more crash proof.
Okay. Are there chances of bird impact?
Not much, I would think.
Not much.
I mean, we have not really come across, and we have found that birds get scared away by the drone noise.
Okay, yeah, that's
so
also...
we haven't really had much of a bird impact situation.
Yeah. So there are a couple of, at least one question for sure is a very important question on the cost implication, but I'm going to hold on to that because that requires a detailed discussion. Once Sridhara is done at 3:25, probably we can revisit these questions. I'm making a note of it so that they don't disappear in the chat window. Thank you again, Professor Satya. We'll tune back to you at 3:25 after Dr. Sridhara's talk.
Excellent.
So,
thank you very much.
Yeah. Audience, please stay tuned. The next speaker in this session for us is Dr. Sridhara Narasimhan. As I pointed out in the introduction, one of the most important things in a country like India is water that is meant for agriculture. Always, it's not about the question is not about availability of water, though most of the time it's about availability of water. But in addition to that, what happens is even when water is available, the question is how intelligently people use it, how wisely people use it. Because, for instance, we are heavy on, as Dr. Satya pointed out, we are heavy on crops like sugarcane and paddy, which are like water-intensive crops. But the moment we start looking at the quantity of water that goes into manufacturing or preparing food or any product, then the whole scenario changes. And in that sort of a context, what I have observed as an individual when I work with people in the villages and farmers is many times their knowledge is like pretty deep in terms of the techniques that can be used for agriculture in small farms. But managing water has always been an issue. And I guess that is one place where Professor Sridhara Narasimhan has come up with an approach which they've implemented. This I know through their talks. I've listened to their talks a couple of times in a village in Maharashtra. And if you look at it, he has used his expertise from chemical engineering, where it's his process optimization and network management. They use that to the application of water networking sort of an situation. I'm sure that he will talk about this in far detail. Over to you, Dr. Sridhar.
Yeah, thanks and greetings to all the audience. Thanks, Parini, for that introduction. Should maybe one caveat is probably needed. I'm going to be talking about rural water supply, and it has a peripheral impact on, it has a, rather, I won't say peripheral impact, it has a significant impact on the lives of people in rural areas. So I'm not going to be directly talking about water for agriculture, but water for human consumption, water supply. And because, as you know, Paini and Satya have been mentioning, the large significant portion of our population stay in rural areas, and therefore, an impact on how efficiently and how equitably you can supply water to our consumers will directly have an impact on the lives and livelihoods of the main cogs in the wheel of the rural economy, the farmers. So before I get started with my presentation, there's a small video and then which I would like to share. Let me see if I can get this going. Share screen. Yeah. Yeah. Okay, so oops. Okay, so let me now. Sorry. Yeah. You're able to see the screen. I mean, sometimes I've noticed people telling me that when I navigate, it's not as smooth. So if the screen is stuck on some slide, please let me know. One of you, me, Naresh or Paini, can let me know, and I will, restart it. Good afternoon and good morning, good evening to our friends from all over the globe. My name is Sridhar Kumar Narsimhan. It could be you could call it Sridhar for short, as Paini called me. I work in the Department of Chemical Engineering, and I'm also associated with the Robert Bosch Center for Data Science and Artificial Intelligence. Yeah. Okay. So this is my email address and my website. Feel free to send me an email on this or any other thing. So when I say WDN, it stands for Water Distribution Networks. We've been working on this area for the last several years.
Sorry to interfere. We are also seeing the notes or the next slide that is going to come up. Is that how you want to keep it?
No, that's not what I intended. Not sure.
Yeah, now we are able to see only one slide, but you just have to go to the full screen.
Yeah. Is that okay?
No, it's gone back to that mode.
Okay, so how about now? Yeah. Is it okay now?
No. At least for me, it doesn't show because we are still able to see the, the other slides on the left, the small icons.
Please make it full screen.
Yeah, it's not the full screen yet.
Yes, slideshow, please.
Yeah, F5 probably just.
Yeah, I'm doing F5. Oh, okay. I think I know why this is occurring. It's because I'm using two screens.
Okay.
Okay, so how about now? Is it maybe it's not the ideal thing?
Okay, that's fine. This is fine. You can just go.
Because it's not as I said, this is not
got
ideal.
it,
but
yeah.
I realize that's because I'm using two screens, and I think that's what sometimes it does that.
Okay, fine.
Yeah, sorry about that.
Yeah. This should be
okay, I think. Yeah, thanks, and thanks for pointing out, Paini. So as I was saying, over the last several years, we've been working in water distribution networks and not just focusing on theory, that is developing theoretical methods for designing water networks, designing the locations of pipes, pumps, valves, sizes. Now, how do you control these networks? How do you operate these networks? How do you isolate leaks in networks which don't have a lot of instrumentation? We don't have a lot of sensors, and therefore it's very difficult to pinpoint the location of the leak. So how do you solve these kinds of problems? So we have come up with what we think are very relevant, these are solutions which are relevant to the Indian and in the context of several of our friends who are attending the talk today. Again, these are very important, but not as well studied in literature. If you open a standard reference in the water distribution networks, either design, operation, or maintenance, they are mostly focused on networks which are the way they are operated in Western countries. So I think that's what, in some sense, makes our work very more topical and local. So all of these ideas we have demonstrated in our lab. We have set up a very complex demonstration facility for testing out these ideas and algorithms. And as Parini also mentioned, we have now taken these right from the lab to the field in the IIT Madras campus and in an ongoing project in Maharashtra, which I'll show you some snaps and some learnings. So these are, slightly dated figure, but things are still not as ideal as they would like to be. So this is the number is, the ground reality of water distribution networks is that there's a significant disparity in how they should be operated. In the urban areas, LPCDs liter per capacita per day, which means one person in an urban area. These are as per WHO and also Government of India guidelines, 130 to 150 liters per person in the urban areas. And more relevant in the rural areas, it's 55 liters per person per day. And the target is that you should be able to cover 100% of your population, meter all of the consumers, and have NRW, non-revenue water. It's basically the difference between the amount of money that you spent in supplying the water and what you recovered. So it includes things like leaks, water thefts, and also water for common use, like firefighting or other hygiene purposes and so on. So the target is that you need to bring down the leakages, which are roughly anywhere from 30 to 50% to around 12%. And more importantly is, you have to guarantee 24-hour supply. The reality is that in many networks, many water systems in the world, is that water is supplied only for a few hours in a day, and the consumer has to, store water. And then that's what you saw briefly in the small video animation that I showed you, where water has to be stored by the end consumer because they get water only a few hours in a day. Most of these networks have very poor level of instrumentation. There's nothing much to tell you how much water is flowing in the pipes, how much water is collected in the tanks, partly because these are legacy systems, and historically these sensors were expensive. And nowadays, it's possible to, I'll show you some examples of how we are able to bring down the cost of these sensors and come up with well-instrumented systems. The Jal Jeevan mission is an ambitious mission of the Government of India, where the target is to provide a functional household tap connection to every rural household, and guarantee the 55 liter per capacita per day. And I think the government is on target to meeting these by 2023 or 2024. And this is one of the most ambitious water supply scheme projects probably ever taken up world over. So what are some of these issues? To summarize, there's a significant amount of water loss due to leaks. The operator does not recover much of the expense because they are either not able to meter everybody, or even they're able to meter, they don't know exactly how much people are consuming. There's not much of instrumentation. The energy water nexus. So again, it's not just energy water, it's energy, water, and food. What that means is a significant amount of the world's energy consumption is on transporting water. Water is again used for producing energy, and again, water and energy are significantly used for growing food. In fact, there's a lot of exports of agricultural products are actually proxies of export of water, because these are water intensive crops. So when you export, say, maybe a kilogram of rice, you're actually exporting huge amounts of water, because a lot of water, virtual water, because a lot of water was probably used in growing these crops. So, there's a lot of, then this is the other significant issue is that, as I said, which I'll point out, is that there's a big difference between how these networks, pipeline systems are designed and how they are operated. Right? And they're operated intermittently, and this results in inequitable distribution. I'll give you some simple examples of and formal definitions of what these things mean. So this is again a cartoon sketch of what a water distribution network will look like. So this is a reservoir where you have, treated water is stored, and this is pumped to these tanks, which are overhead tanks. And from the overhead tanks, water is usually, flows by gravity to the end consumers, in their houses or in their stand posts on the streets and so on. Now, in this dotted area is what I call the supply side, and the other area is called the distribution side. The distribution is where how the consumers are taking water, the consuming water. Right? So the dotted line in this right graph over here shows what happens if water is being supplied continuously, which means when the person turns on the tap or the faucet, water is coming in, and that is because there is pressure in the pipeline and there is enough water in the pipeline system, so that whenever they open the tap or faucet, water flows into their bathrooms or the kitchens or sinks or the buckets. So this is how most water networks are designed to operate continuously, which means there should be enough pressure in the network and in the system and water in the system, so that when you open a tap or faucet, you get water. But however, that is not the case in many parts of the world. What is supplied is called intermittent supply, which is shown by these orange colored boxes, which means water is supplied only a few hours in a day or a few days in a week. So which probably means if water comes in the morning, then the customer or the end user or the farmer or whoever it is has to store that water. It could be, it could be in large concrete sumps or overhead tanks or plastic tanks, or if they are not so fortunate, then it has to be stored in small buckets with utensils and so on. So that is basically the difference between continuous and intermittent distribution, supply and distribution. At the supply side, again, how water is, because of these large overhead tanks. In the rural areas, typically these are, a tank is sized so that it holds around, third to 50% of the day's capacity. So you can imagine that a tank would probably be filled completely and emptied twice or thrice in a day for water supply in a rural area. So in this case, what that means is the pumping station, the water again could be supplied always continuously, or it could be supplied intermittently. Valves could be opened and closed so that these tanks are filled and emptied at different points of the time. So now again, there's a point out the difference between how continuous operation and intermittent operation. I gave you simple examples. I mean, in continuous operation, you open a valve and then that changes the pressure, and because the pressure changes, it affects the outflow rate. In intermittent operation, you open a valve, it changes the pressure, it changes the outflow rate. However, because this is intermittent supply, water has to be stored by the consumer, so it can only affect the level of water in a sump or a tank. In continuous operation, the pressure, pipelines have to be pressured all the time, which is not the case in intermittent operation. So in intermittent operation, the pipeline is not pressured all the time. And in continuous operation, you need to be able to continuously control the network, which means if the demand increases, right? Usually, there are two peaks that are observed in a day, in the morning and in the evening. So which means there has to be enough control or flexibility in operation so that whenever there is an increase in demand, the water can be supplied. In intermittent operation, however, you could store the water because you're not supplying the water at every point in time, but only at certain hours in the day. You can supply more than what you need, and that is stored. That's exactly what happens in the tanks. And therefore, you can store the water and use it later. So there is some amount of flexibility which is not there in continuous operation. In continuous operation of the pipeline, for some reason, some pipeline is burst or the water supply is disrupted, then the people don't get water. However, in the intermittent operation, there is some flexibility because the consumer has capacity to store water. And there's a lot of reports about quality. I've not talked about quality over here. So there are a lot of reports saying that continuous water supply actually improves the quality of water that is supplied, because the water is not stagnant. There's always pressure, and it is in some sense replenished through continuously. There have been some studies which point out the quality in intermittent supply is actually lower because the water is stagnant for some time, and that it affects. There can be other kinds of biological growth, or water could seep into the pipelines, dirty water from outside, and so on. So there are some reported literature. I'm not going to talk about quality, but another point of view, to contend that is that a lot of the contamination actually occurs at the customer end, at the end point. It doesn't really occur at the pipeline level. It actually the contamination occurs at the at the customer end. So this is something which we need to clearly understand and have an answer to that. So why is there such a poor performance in the network? I mean, when I say poor performance in terms of how much water you wanted versus how much water you get, why are the leaks, and why do you get water only for a few hours in a day? Even though the network was really designed for continuous operation and was at the time of design, these networks are designed keeping in mind a 20 to 25, 30-year horizon. So they also anticipate population growth and usage growth and so on. And yet there is a difference in performance. One of the significant factors is that these infrastructure is aged. So there are pipelines have become old. They started to leak. The tanks leak, and they just cannot supply and hold enough water. The growth at the time of design, they assumed a certain growth pattern. The growth ended up being much more than what was projected. This is especially true in many Indian and other countries, cities, and even rural areas in many parts of the world. There could be inadequacies in design because the designs were probably not done on a very scientific or rational manner. And that could be, of course, the most important thing that Paini mentioned. There's not enough water at the source. So this is as far as the infrastructure is concerned. In terms of during operation, you see what happens is most of these networks are operated manually, which means there are, as you saw in that small video, there are people who go around opening and closing these valves manually. And surprisingly, even though we are all human resource rich countries, the network operator may not have enough manpower employed to operate these networks, because they're just not generating enough revenue to be able to employ and pay these operators. And the networks are probably not operated very rationally or scientifically. They're operated based on heuristics and or experience, or what they think is the best operation. There is limited amount of instrumentation. There's not much of communication and coordination and feedback. A classic example could be, water is being filled into a tank, but there's not nobody has. At some point it starts overflowing, and then the person comes and closes the tank, valve to the tank. Or it could be that sorry. Yeah, or it could be that, sorry about that. It could be that the water is, the tank valve to the tank is open, but water is not filling in, it has run dry. All of these are basically because there's limited instrumentation, communication, coordination, feedback, and therefore there's not much of control. The most important factor, I would say, to summarize, is that they are designed for continuous operation but operated intermittently. And that is simply because of several other issues, and therefore this affects the final operation of the network, and this results in inequitable supply. What that means is some people end up getting, because water is now supplied only for a few hours in a day, so everybody tries to open the taps and fill their tanks. It's a natural human tendency to do that. And at that point in time, there are, of course, if you think about it, people who see a higher pressure and versus somebody who sees a lower pressure, if they open the taps at the same time, the person with the higher pressure is going to extract more water if water is supplied for the same amount of time. So this is called inequitable supply. So our approach is been to, as I said, a lot of these networks are operated manually. So to retrofit these electric, and this is to account, and this is as I said, there could be limited manpower available for operating these. Secondly, these are not, this is not it's a tedious job. It's also a physically demanding job. And therefore, these are very large diameter pipelines, anywhere from 200 millimeters to thousands of millimeters to maybe 1,000 millimeter pipelines, and the valves are not easy to operate, especially when water is flowing under pressure. So our approach is to retrofit the existing manual operated valves with electrical actuators. Install flow meters or level sensors, and ESRs is elevated storage reservoir, GSR is ground storage reservoir. So again, we are looking at frugal sensors. We are also thinking about how to replace flow meters completely with other low-cost sensors. Because one of the standard complaints that we get is flow meters go bad after certain years of operation, and can we replace these with frugal, cheap, low-cost sensors? Can you use low-cost, low-power consuming IoT, stands for Internet of Things? The Internet of Things idea says that just as we are all connected on the internet, all these sensors, actuators, valves, devices, they'll all be connected. So it's an internet of everything now. It's not just Internet of Things, Internet of everything. And these will be used to schedule the water supply. And when I say schedule, it means supply how much water to when. And now, because of you have retrofitted these valves with electrical actuators, and we could, in principle, by switching on by the flick of a switch, you can open a valve, close a valve, or use wireless tools for communicating. I see several of you are now joined in from a wireless connection. So you can use these, as I saw in the sketch, in the short video. The operator can just open a valve or close a valve from the comfort of their office or the pumping station. So they don't have to travel tens of kilometers in the dead of the night or to remote locations where these pipes are laid to open and close these valves. So what are the advantages? The advantages are that you can schedule, you can come up with a schedule of operating these valves and pumps so that you are able to meet the demands of your end consumers. More importantly, they can be implemented reliably, which means that if you want a valve to be open for 1 hour, let's say now time is 3:11 in India time. If you want the valve to be open now at 3:15 and the valve to be closed at 4 o'clock, you can implement this reliably. All said and done, if you involve humans in the loop, even a 5-minute delay here or there could lead to water either overflowing or wastage, or a tank running dry. Now you can come up with these schedules so that they are efficient, which means they minimize energy. The pumping cost accounts for nearly 25 or even 30 to up to 50% of the operating expenses, and electric power power charges, and these are not domestic power. These are not domestic. In India, there are different tariffs, and many parts of the world, there are different tariffs for domestic and non-domestic consumers. Domestic consumers are subsidized, and these don't come under domestic tariffs. So the tariff for operating these pumps is much higher. If there is a gravity-driven network, you could finish the job and reduce the time of filling. So whatever it took 3 days, in principle, you could, also not 3 days. What could happen in say 9 hours? I'll show you an example of whatever could be done in 9 hours could be done in 5 hours. You could ensure equitable supply. Publish these schedules ahead of time, and then because they reliably now can be implemented, so people don't have to stay up at odd hours waiting for the supply, and they know that if the operator tells them at what is going to come in at 9 o'clock, they know it's going to come exactly at 9 o'clock. Okay, so this is what I mean by optimal operation. I'll skip over these, and then so I'll give you some simple examples of case studies. So this is by our collaborators in the Tamil Nadu Water Infrastructure Company. It was for a water supply to it was for a peri-urban area, but it could also be water supply to a multi-village scheme, which is very common, where a single source supplies water to several villages. So this could be T1 to T9. You could think about these as different villages, and each village has a tank, and water is supplied by this common source to this tank. And then from these tanks, the respective villages, they open the respective village. There is somebody who is employed to supply water to the tank. So the optimal schedule looks something like this. What that means is the way to read this is for the first 30 minutes. So let's say now time is 3:15 here. So for the first 30 minutes, you supply water to villages 1, 6, and 7. Then for the next 1 hour or next for half an hour after that, you close these valves. Why do you close these? Because there's probably enough water over there. If you had not closed these, the tanks may overflow. Then for an hour, you again reopen the valves and and supply water. Then for 30 minutes, you supply water to 4, 5, and 6. Don't supply water to 1, 2, and 3 because there is enough water over there. And therefore, you implement this over the entire day. And what we have shown is that this will give you result in the lowest energy consumption. It's around 5,000 kilowatt hours. And the entire operation can be done in about 20 hours. The standard, how do you know? We know that this is the best you can do with the system. More importantly, it can be done with the existing system. You don't need any large scale changes in the system. All we need to do is with existing valves, butterfly or sluice valves, you put an actuator on top of that. Or if you are able to convince somebody to operate these as per the schedule, you can expect this kind of lowest energy consumption around 5,000 kilowatt hours. It can also be done in the lowest possible time around 20 hours. So this is an example of rural water supply scheme which we analyzed, which is from a book by Professor Bhave and Gupta. So this is a classic example of what happens when there's a big mismatch between demand and supply. So this is properly designed. There is no problem in design in this particular thing. So when all the tanks, when this is supplied, these are all the 1, 2, 3, 4, 5, 6 villages have to be supplied water. The demands are all in cubic meters per hour, assuming water to supply it for 8 hours. Now what happens is if you open the valves to all of these tanks at the same time, there are some villages which end up getting more water, 18 cubic meters over here, as opposed to 10 cubic meters. There are some who are getting 40 as opposed to 6. And remember, these are designed to get 6 cubic meters, but end up getting 40 cubic meters. There are others who were supposed to get 9 cubic meters, but end up getting only 0 cubic meters, likewise these villages. And the reason this happens is because when you open all the valves at the same time, the pressure over here at this guy over here was so high that it ended up filling at the water tank at a much higher rate. Even though it was designed to fill at around 6 cubic meters per hour, it ended up filling at 40 cubic meters per hour. And because as long as this continues, the other guys over here hardly get any water. So therefore, you need to be able to shut off or control the water supply to this guy, in order to ensure that the water is supplied to the other villages. And this could be done, in the interest of time, I'll just skip over these. This could be done using control valves, which means you keep the, or you could do it using, on-off valves, which just means existing valve, you open a valve and close the valve. And you could still end up getting a reasonably efficient way of doing it and supply the water in roughly under 8 hours. So this is an example of a multi-village scheme, which is data was collected from our friends in IIT Bombay, and they had analyzed this network. There are lots of problems in this network. I can encourage you to look at their site. It's called Sitara Center for Technology Alternatives to Rural Areas. And they have analyzed the scheme extensively and found a lot of shortcomings in both design and operation. So they analyzed, they went to the field and found that this network was operated in a certain manner. And they saw that water is being supplied for around 9.25 hours. Now this is how it looks like. Right? So this means that the first 2 villages over here get water for 1 hour, 15 minutes. Then after that, in this villages Nalde and Naldewadi get water for up to 2.25 hours, and so on. Now, so the question that we asked is, if could you supply the same amount of water in a less amount of time? Now, by a different sequence of operation, and we answered this, and it turns out that you can supply the same amount of water to all these villages and supply it in 5 hours. Now, what does that mean? That means if you are ready to operate the network for 9 hours, you can actually increase the supply by nearly 80%. And in this case, this was not a case of constraints in supply because they had access to a perennial water source. So again, the point is that sometimes these networks are not operated efficiently, and there's a lot of people don't get water, not just because there's not enough water, but even if there is water, it is because these are not operated efficiently or correctly. So if you had operated these networks in a slightly different manner, you could actually supply 80% more water. The only requirement, of course, is there's no free lunch, so to say. You need to have more control over the network. You need to be able to send people or retrofit these valves and operate these in a more efficient manner. So this is a photo of a network that I mentioned that we have in a lab network over here. It could be used to simulate or realistically create physical simulations of real world networks. Sorry. So it's a well instrumented network, and encourage all of you if when it's given an opportunity. We will also try and put up some of these. We have some ideas about how to share these network experimental facilities with the rest of the world. So the idea is that you have these 5 tanks over here. All of this till now what I was talking about was simulation. So you could ask how realistic are these. So we actually verified these by filling these tanks one at a time, and it turned out it took 3,700 seconds, slightly more than an hour. And you come up with an optimum schedule, it's really 2,200 seconds. And therefore, what we're talking can be implemented in practice. We also have a scheduler, which is web accessible software. This is currently, we are upgrading it to make it more user-friendly and in tune with the latest IT technologies. And I'll also share the link of the software system. But as I said, we've taken these ideas from the lab to the field. These are photographs of what we have done in the IIT Madras campus, where retrofitted existing valves with electrical actuators, put level sensors in the storage reservoirs, use wireless tools for communication and control. Over here, I'd like to point out that as I saw that, as I mentioned, wireless has now changed significantly, made a big difference to our lives in terms of how we communicate, how we do transactions, how we work, and a lot of this because of the GSM or the cell phone technologies. Now, in principle, you could use these existing cell phone technologies, both now let's talk about 5G, and which allows you to have large numbers of devices and with very less what's called latency. However, all of this requires that you need to have you need to pay a bill for a connection, and every connection you need to pay money, and the network has to be up all the time. So there's an alternative protocol or technology called LoRa, which works over long distances. More importantly, it is in some sense it works. You don't have to pay spectrum usage charges. It's free to use, and that's what we have decided to use for some of our water networks, especially in rural areas where you can deploy these at extremely low cost. More than that, the cost of the energy, any of these sensors, when you use in LoRa, they consume much less power, and the devices are also much more energy efficient and low power consuming. Okay, so these are again some more photographs of the field installations. This is the valves and retrofitted electrical actuators in the IIT campus. This wireless box allows it to receive the commands to open and close a valve. A lot of people have used LoRa for monitoring water networks, for monitoring agricultural systems. We have also used this, shown how you can use LoRa not just for getting data, but actually opening and closing valves, so-called closing the loop. These are the actuator dashboards and so on, where you can get this display on a desktop or in a mobile phone even. So this is come to the nearly end of my presentation, and this is the water, the multivariate scheme that we are implementing a lot of these ideas. This is a joint project with IIT Bombay. It's a multivariate scheme supplying water to around 17 villages. There are a lot of problems with these schemes. One of the problems is that certain villages don't end up getting water. As I said, that's so-called inequitable supply, and therefore a common demand during such situations is to relay the pipeline. However, pipelines are really expensive, and it's not. So what we are going to demonstrate is by different schedule, can we reduce the inequity in supply. Likewise, there are certain days which there is during power, there's a shortage of, there's a power, when there is a power cut, there may not be water is not supplied. So idea is, can we supply water a day in advance, and because of these scheduled operation, it can be implemented in a reliable manner. So these are again at the Safale, this multivariate scheme where the existing valves have been retrofitted with electrical actuators and can be remotely operated. So the water tank, the top of water tank level sensor, which is powered either by solar power or by conventional power, and these are extremely low cost. The user interface which tells you what is the water level at the different tanks, and can also be used to open and close valves, as I said. So just to conclude, this is some of our ongoing work in, not just in the theory, but also making software and product devices. Our aim is to make a difference to theory and practice. This I'll acknowledge a lot of our funding partners here from IIT Madras, the Robert Bush Center, Department of Science and Technology, and all our collaborators and friends who made this possible. Thanks to Siddhi and the Global Engagement Office and AARDO for giving me this chance to talk about this work. And I'll be glad to discuss and share and share experiences most importantly, and learn from you also. Yeah, thanks. And I'm Parini, over to you.
Thanks, Sridhara, for those detailed and inspiring presentation. So, should we take questions? No, maybe what we'll do is we will go back to Satya's question. In the meantime, if there are a few questions for you, there are just a few questions, so you can probably take a look at the questions, Sridhara. In the meantime, we'll address Satya's questions and come back. The questions that were short for Satya earlier. So Satya, now the question is for you. Yeah. So one of the questions to you, Satya, was can we talk a little bit about the cost implication, including supplier of these drones?
Right. So there are two models about this, right? So one is a ownership model, the other one is a service model. Typically, if you look at the implementation that's happened in China, it's more like service providers actually providing service. And even in India, for example, farmers try to appoint spraying people. In the manual spraying case, there is a labor cost associated with it. The farmer will get some pesticide and then give it to the spraying person, and then they will spray. I think what we understand is that the service provider model is the one that will eventually happen, and the ownership model is probably going to be useful for like corporate farms, where the corporates can actually buy these drones. So if you have to buy one of these drones, it would cost somewhere between about 5 lakhs to 10 lakhs rupees, I would think, because it's actually fairly bulky and it requires some instrumentation and so on. But I think more pertinent is what is the service charge question. What we have understood from the field is small farmers to medium farmers, when they are hiring farm labor and procuring pesticides to dilute and spray, they are spending anywhere between 200 to 600 rupees per acre of spraying, and this depends on how small the farm is. Like small farmers actually end up paying more on a per acre basis, because ultimately they are paying on a daily wage basis. So the same wage actually works for both a small farmer and a large farm. So on a per acre basis, the small farmer actually gets hit more. So the quick answer finally is that we have made calculations and found that it is possible with drones to offer spraying at the rate of 200 rupees or under 200 rupees per acre. And that is definitely much smaller when compared to the multiple more times that farmers end up spending on manual spraying today. So that's a very good sense of what's the kind of cost involved, and this absorbs the capital cost, everything over time. So if a drone were to last for about 5 years, a service provider procures this and then operates it for 5 years, maintains it for 5 years, and he should still be in a position to actually operate it for about under 200 rupees per acre and make a profit. That's what we expect. Did you get that?
No. Okay, yeah, sorry. So that's a more sensible way of looking at how to deploy such techniques, especially because the basic infrastructure cost is going to be more for a small farmer, cannot afford about 5 lakhs. And yeah, the service model seems, I mean, this is the first time I'm listening to this part of your talk. The service model seems to be, should be an appropriate model for the Indian farmers farming scenario. Okay, so the next question for you is, have you noticed plant toxicity due to more concentrated pesticide use? I think you already sort of addressed this question.
Yeah, I sort of addressed. So a quick answer is yes. I think if you we don't really have very commonly available drone-specific formulations of pesticides yet. So we do dilute, and so if you directly use it without dilution, it will actually affect the plant, is what we understand. So we do dilute it up to about 10 liters for 1 liter of spray. But this is a specific formulation that we have handled. There are varieties that are coming up with more ultra low concentration, spraying and so on. So this is an emerging field. I think the chemical companies will be better at answering this.
Yeah. So a very related question, I guess the answer is yes. Are there organic herbicides, pesticides, and fungicides?
Oh,
if
indeed,
they are
yes.
there, you can spray, right?
Yeah, all we need is a liquid that is less viscous enough for it to push through the nozzles.
Yeah, I think that should be the question, because here the question is actually typed as, are there no organic? That part we are not sure, but if it is there, we can.
No, I think the person who is asking the question might have actually felt that the talk was more predicated on pesticides, which are typically inorganic. And I think the point is very well taken. So the quick answer is yes, organic pesticides are available.
Okay. So the next question is, do these drones have an altitude hold mode?
Yes, that's actually a very good question. So the altitude, I think can you just complete the question?
And then the second part of the question is, are they computational?
Correct. Right. So that's what actually made it more interesting.
Okay.
So what you actually do in a drone today is to use a 1D lidar, right? So the 1D lidar is always sending like a laser beam, an IR beam to the ground, and then getting it reflected back in order to sense what the altitude is. And yes, the flight controller is enabled to do an altitude hold mode, and that's important in this case because most of the crop is typically of a more or less uniform height, and we are looking, and let's say for example a relatively grown crop could be of the order of about a 1.5 meters high from the ground, and we would still want to actually spray at another 1.5 meters above the crop top. So that's a particular altitude that we would want to maintain, and we do indeed have an altitude hold mode by which you constantly ping the ground with the laser beam and then get this back and then do a calculation on board to find out whether you're holding the altitude or we need to change. So this keeps on happening all the time, and it is computation based. The problem is this is now crop specific. So if I had a crop where each crop is like a plant, right, and the next crop is a little farther out and then it is having a canopy. These canopies intersect at some points, but they don't intersect at other points. You will have gaps that are showing the vacant land versus its canopy that is reflecting the laser. The drone will actually end up will go in a humpy manner because the laser is actually pinging either on the ground or the canopy or the ground or the canopy and so on. And it gives you some kind of an average data on the altitude that keeps varying as the drone keeps going. So we have found it a little bit difficult to do an altitude hold mode, particularly in slopey terrains of tea plantations, for example, right? But so there is like a lot more tuning that needs to be done, and we could probably have to deploy artificial intelligence to understand that this is the terrain, and therefore you need to do something like this and so on. So more work is required under those circumstances. But for more dense crops that are more uniform and so on, this is not such a big issue. As you can see, there are no simple answers.
Sorry. So the next question is sort of a very overarching question. So it's great that technology is being used in the agricultural sector in India, and it's advanced. The question is how to use this technology to overcome negative impact of climate change on agricultural production.
So I think I will still take this question in the specific context of what I talked about. Or the quick overarching answer is that we always have to be looking at the environmental impact and sustainability in pretty much everything that we do today, right? And definitely in crop spraying as well, we have to be sensitive to this particular aspect. So the response here is twofold. One, we are actually using electric drones and not combustion powered drones. at the moment, right? So this impacts the range and therefore the number of acres you can spray, in a single charge of the battery. And as battery advances actually improve, we will be able to project further and further on the number of acres you can spray in a single charge, or we will have to build bigger drones to accommodate larger batteries for that purpose and so on. But in general, we found that electric batteries are still cheaper because electricity for recharging the batteries is actually pretty inexpensive when compared to if you were to use combustion and fuel for it and so on. So from a cost perspective, as well as environmental perspective, electric drones is better right? So when compared to a corresponding combustion thing. The second, because we are not using a lot of water for dilution, we are actually saving on a lot of water. A point that I want to dovetail to Sridhara's lecture on saving water, and we will actually be ending up saving enormous amount of water. About 90% water that goes into spraying pesticides will completely be saved, and that's a huge thing for environmental impact. In effect, I think the technological development that we are talking about is going in the direction of environmental sustainability.
All right. Yeah, I guess those are the sort of questions for you. And I mean, just for the sake of knowing, what are the other things that you do in terms of application with respect to the drones?
Yeah, I did touch upon that in one of my early slides. So drone applications in agriculture are for mapping, spraying, seeding, and the last one is surveillance. Right. So except for seeding that we have not gotten to yet, we are in the position to do all the other three.
Okay. So I also remember that you told that one is about generic spraying and the other one is like spot spraying.
Correct.
I would assume that there is a little bit more technology that is involved in the spot spraying. But what is the level of confidence in being the reason is I visited one coffee plantation and then I realized that the pepper leaves, they practically hold each leaf and then they spray on it. Okay. Right. So I mean, that was unimaginable for me, like tens of thousands of leaves, but then they go around spraying that. So in such a situation, is it possible at all to do such a thing using a drone?
Indeed, I mean, at some point in the future, yes. I think what currently is the challenge is a couple of them. One is, first of all, positioning the drone accurately, right? So we are still looking at GPS to do this, and GPS has like about somewhere between like a 1 meter accuracy. You can use dual GPS and bring it down to centimeter level, right? But even if you actually try to locate the drone still actually shakes a bit. Right. So and so it needs to be stabilized every time and so on. So from that perspective, there is a challenge there in localizing the drone. The second is to identify where we need to spray. So one implementation that comes to mind is if it's possible for us to actually have a boom in the forward direction that holds a camera that watches the crop and then looks for where to spray, right? And that we need to actually do an onboard edge computing with some image processing and AI in order to be able to figure out where to spray. I think I've not come across people who have actually implemented this idea, but that idea exists around. Yeah.
Okay, so thanks again, Professor Satya. I don't know how to clap for your presentation, but virtually, I guess we thank. It was a fantastic presentation. Thanks again. And please feel free to type questions. If we have time, we will take those questions. Otherwise, I can always send out an email to him and he will respond.
Can I make a small comment?
Sure.
Okay, my name is Dr. Rajesh Valdam. I'm from the African Asian Rural Development Organization's headquarters. Now, as we know, Professor Satya, this title of this e-training is Affordable Technologies.
Yeah.
Now, my only a concern or summation or comment is that how do we see down the lines transfer of this technology to the African countries in terms of its affordability and in terms of its sophistications to the kind of manpowers which African countries have?
Right. I think let me answer that question in a couple of ways. One is, I think I did give the economics in terms of like service provider model, and if you get to the bottom of what I finally said, today Indian farmers are paying anywhere between 200 to 600 rupees per acre of spraying, depending upon what the size of their farm is, because they are actually giving daily wage to the spraying person who is spraying manually. So the small farmer actually ends up paying more per acre than the large farmer. That's an ironical part. So when compared to that, our calculations for a 5-year asset holding by the service provider, it's possible for the service provider to actually offer spraying services for under 200 rupees per acre. So which is actually lower than the lowest of the range that is currently happening. And so if I were to actually transmit this to the African scenario, we would still
Yes,
be able
yes.
to say that this is actually cheaper than anything else that is currently available. That's the quick answer on the cost part. The second thing is we are actually trying to do this in a way where we don't train pilots for this purpose. Okay. So in fact, right early on when we started this, we did go to a farm of a friend of ours, and he was about 72 years old, and we were actually wanting to use that farm for shooting something like an ad, right? So I mean a modeling kind of thing. So we use a drone. So our drone pilot was actually trying to ram this drone against a coconut tree, and the drone went near the coconut tree and refused to go closer, right? Because it can actually sense the coconut tree as an obstacle, and then it stays away. And as he was actually, and then the farmer was actually curious. He said, "Can I actually operate it?" And we said, yeah, why don't you do this?" And in about 30 seconds, we actually gave him instructions on the controls like left, right, and stuff. And then he started. He was actually, really upset that we were doing a lot of maneuvers closer to the ground against the coconut tree and all that stuff. He didn't understand what we were trying to do. He wanted like an aerial view, so he wanted to fly pretty high. So he just slammed the controls, and then it went up, and it goes through this coconut farm's branches and stuff, and there was breeze that were fluctuating the branches. Our drone was actually trying to negotiate through these shaking branches in the breeze, and the farmer was completely oblivious of this, right? So which essentially means that if we have a significant amount of obstacle avoidance detection and avoidance, a simple farmer should be in a position to handle it. We have further waypoint navigation and path planning, and then we can have the rastering, the geofencing of the farm. All of these things can be automated, and we can try to come up with a software front end on a laptop or whatever, or even a mobile phone maybe, which will allow for a farmer to operate without having much training on using this, which essentially means that you don't really have a technological cost to a labor cost or so, which could be pretty high. Or the service provider will have to include under his 200 rupees per acre, right, for providing a pilot, right? So we have factored that also, and so in some sense, this is actually extremely affordable, and I think we should actually break this notion that anything high tech will be expensive. That's not the case here.
Yeah. It's really very encouraging and very interesting answers also. Do we have some companies from India operating in with this kind of a perception, African countries? Any ideas, sir?
I think there are a few of them, not a lot in India at the moment. We are doing demos on a request basis, and we will be happy to get on a demo, and then if people are interested, we can actually supply more, and we will have to then identify a service provider who takes it up and so on. So we will have to evolve this model in Africa. Yeah. We'll be happy.
We get in touch with you. Yeah. Thank you very much, Professor. Thank you.
Thank you. Thank you, Professor Satya, again for that wonderful talk and the the question session. Now over we will go to Sridhar and Dr. Sridhar. Questions for you? Yeah, I request the participants to be on mute, please. Yeah. So Sridhar, here are your questions. One of the first questions for you is, what is the maximum age of the infrastructure? Probably the network infrastructure. That's the question.
So, well, typically these are designed for around 30 to 40 years, and then a lot of infrastructure has to be replaced after that. In fact, in our campus, for instance, we are now, there's an extensive program to replace all the pipelines. So, and of course, if there is it may have to be replaced earlier than that because of several reasons. One could be that growth is exceeded projections, or it's probably too expensive to make, probably cheaper to just replace the pipelines than fix a lot of leaks that exist and so on.
Right.
So there's no one answer to that, but typically you should expect pipelines to last for in the order of decades.
Okay. And why are your electrical actuators exposed?
Okay, so these are again just to show that at the time of these are photos taken at the time of installation. So yeah, they are covered, and because they're covered, I could not show you the lot of the. So thanks.
Yeah,
they are covered.
Housed, but what type of pipes do you use for your water capture?
So the pipes are, I mean, we are not doing any replacement of the pipes, but typically they are, pipes come in different materials, concrete, DI, GI, and HDPE nowadays. For instance, our campus now, HDPE pipes are being used to replace the old pipelines.
Right.
So we are not, our things can work with any kind of pipe material, which is standard.
So as we design water supply, we consider the source. So how would you assign the source depending on the water source?
Yeah, it's not very clear what.
No, not very clear. So engineer Seong, you can either ask the question or you could probably type in the question. You can, I mean, if you're available, you could just unmute and ask the question, or you can type the question as we move on to the next question. Okay. All right. So is the electric grid load balancing method, can it be applied to village water distribution?
Yeah, a lot of similarities are there between electrical networks and water networks. One advantage which is not there in the electrical networks, as I said, especially there's a lot of storage available in electrical networks, unless nowadays I talk about local supercapacitors and so on to temporarily store water. But as I said, one difference is that the storage capacities that are available are very large. For instance, in rural networks, tank size to store anywhere between third to half a day's consumption. So that is one big difference, which means that water can be stored and used later on. So that buffering action is there. It's a significant amount of buffering action is there. So there are, so for instance, we do try to explore different similarities and differences between different networks such as electrical, gas, and water networks. There are some commonalities, but some differences also.
Yeah. So I believe this question, what he tried to ask was, as we design water supply, we consider the source. So how would you assign probably the water distribution depending on the water source? So you spoke about people being in the downstream, or people with a higher pressure might take advantage. So how would we decide? So unless we know what is the amount in the source, how would we decide?
So at the time of operation, as I said, because even though the network was probably, there's nothing wrong in the design. If at the time of operation, certain people end up drawing more water, then there has to be some amount of control which is needed. So one way you can do this is by opening valves to a certain amount of time and closing it for after a certain amount of time. That has to be, that's what the analysis will finally tell you, how long a particular group or a village or a tank needs to get water. If I understand that question. The other is, of course, at the design stage itself, what was the source, the location, and the network topology? Those are interesting questions, and we are trying to answer some of them to see whether at the design stage itself, are there decisions that you could have made or avoided which would result in reliable and robust operation subsequently.
Okay. So the
that's
one
an important problem in the sizing and sourcing and so on. Yeah.
So the one question that I had from your, from your implementation perspective is either by yourself or through with your friends from Sitara when you try to do this. Doesn't the culture of people play a major role when you say that you really cannot use it more than this particular amount of time and stuff like that? Like, I mean, it's all great while we talk about equitable supply, but when we implement, isn't there the culture plays a very important role for people to appreciate that? How did you address that?
That's an interesting point. In fact, that's something which we are going to have to face, which in this particular case also. So because then, as I said, there are different actors over here, and all of them have to be somehow brought on to the same level, and therefore, for instance, in the equitable supply, right? When you try to restore equity, it's possible that some people will end up getting lower than what they got earlier. So you have to get their buy-in, and one way to, it's not an easy task, and that's where the non-technical and the social aspects come in. So in this case, for instance, our approach is always has been to get the buy-in in a gradual manner. For instance, we don't show that's why one of the ways in which we want to get their buy-in is to improve the current operation at the time of there are power cuts. Right? So this is something which everybody gets benefited. Right now, if there's a power cut and nobody gets water, to a situation where there's a power cut, but everybody gets some amount of water, which is better than that. So we need to have a constant dialogue with the stakeholders, and there are multiple stakeholders, and there could be conflicts, and that's an interesting problem, and that has to be negotiated and solved. In an ideal situation, a single operator would be in charge of the multi-village scheme, but again, there are multiple actors over here, and that's a difficult problem to solve.
The other question is you partly address that, with the invention of cheaper sensors and all that. These are getting the entire implementation cost becomes less overall. Yeah. But what about the reliability of the systems? Are they getting better?
Yeah, I would think that's what we are trying to also get, not just the costs, but also improve the reliability of these sensors and see whether there are different kinds of sensors or different, can you fuse data from different non-conventional sensors also to improve the overall reliability. So, to use the correct, what would have called, data-driven models, now you would use a more contemporary word, machine learning, can be used to improve the overall reliability of these systems. And sensors are getting cheaper and more reliable also.
More reliable, yeah. Okay. So from your initial experience of working with the different stakeholders, what is your overall experience? I see always we are like academicians, go with ideal ideas, but then when you go on the grassroots level, the situation is different. So in that sense, how did people at the grassroots level took to this concept of sensors and managing the water?
So that's good. That's a very interesting point. So when I joined IT in 2008-9, at that time, I had not worked on water distribution or water supply earlier on. And of course, I came up with, because of, as you said, my expertise and experience and working with optimization. So this seemed to be an interesting problem to tackle. At that time, our apprehension was again likewise that there would be a lot of lack of cooperation from the end users, either because of fear of automation replacing jobs, that's enforced redundancies. We thought that would be a significant factor that we'll have to account for. Second is how comfortable are the end users with technology and so on. And we are very pleasantly surprised that in both of these situations, as we talk to people, over the last several years, the reactions have been very different. So now the end stakeholders, when we went to scouting in this the Safale project, when we were visiting potential sites for where the implementation could be done, one of the requirements from the stakeholders was increased automation. So they were very interested in having these automated and at a level which is relevant. Not too high, not too low, but at a comfortable level. And we think, in our opinion, that what we are suggesting is at the correct level and so on. The second is, as I said again, the comfort level of operators. So one of the first valve actuators that I showed you that we had retrofitted around 4 to 5 years ago, and several years ago when we had talked about automation to our engineers, right? At that time, there was a skepticism of whether our operators would be able to operate these and so on. But because of cell phone now, cell phone has now become ubiquitous. And the moment we showed the electrical actuator, the question was, can you give me an app to operate this? So from extreme skepticism to at that time we were trying to come up with an app, but as I said, we wanted to take it step by step. Tell the operator that you don't have to now use a T-pipe at 3 o'clock in the morning to open a valve and close a valve. All you just need to do is switch on, flick a switch on, to request from the stakeholder to give them an app where they can operate the phone. That's been a very refreshing and change.
Okay. And you believe we might be able to incorporate transparency into this, and it will
exactly
help.
So so that's another point about this. When you talk about equitable supply, I forgot to mention. So one thing that comes out of all of this is you get the data, right? So now when now let's say there are two users and one of them says they get more and they get less. It's only she said kind of problem. Now data is the best sunlight. Right? Now you have data. Now you really know what each person is getting and what each village or each tank is getting, and therefore data is, as I think, sunlight is the best disinfectant. Likewise, data would be will play the role of sunlight over here.
Yeah. So one last question: is there any tool to remotely sense water leakage in water?
Exactly. Yeah. So that's something which I didn't talk about. Water leakage over here, which was focused on supply. Yes. Once you have all of this sense data, it is indeed possible to detect. An immediate pipe burst is, of course, something which manifests. It bursts on the road. I mean, you can see the water gushing out from the road and so on. But slow leaks which accumulate over time, it's possible to indeed detect these and track these leaks over time. Yeah, it is indeed possible.
Okay. All right. Thanks, Dr. Sridhara Narasimhan, for this wonderful presentation and the discussion after that. I guess we covered almost all the questions. Not almost. We covered all the questions. Thank you very much. And it was an inspiring talk indeed. Thank you very much. Yeah, so the participants, please thank them. Thank both the speakers. And thank you, AARDO, for the wonderful opportunity to having given us a chance to listen to these two researchers. Naresh, over to you.
Yes, sir. I would also like to thank both the speakers of the day for the detailed presentation. And I would also like to thank our moderator of the day, Dr. Palniappan Ramu, for managing the session very efficiently. With this, we'll end the day one. Before that, I'll just share the tomorrow's plan. So tomorrow we'll be having the topic technologies facilitating access to value chains and markets by Dr. Satyanarayan Sheshatri and Major Ved Prakash, CEO and co-founder, Gratitude Forms. And this session will be moderated by Mr. Srinivas Chigulapalli, a project officer, RUTAG IIT Madras. So with this, we'll end day two. I would also like to thank all the participants for making the session wonderful. Like I hope, I mean, seeing the chat box, I can see like everyone is enjoy. I mean, like everyone found the session useful. So with this, we'll end day two of this session. Thank you.